If you're looking for an episode sharing the atmosphere of OpenSource Summit North America, then this episode is for you. Welcome back to the Is It Observable YouTube channel. Today's episode is going to be a bit special. It's going to be related to the conference OpenSource Summit North America that happened a few weeks ago in Denver. During that conference, I selected a few speakers that are of course covering more or less topics related to observability. So we'll have topics about observability of 5G networks, so very interesting topics which I'm not familiar in particular. And otherwise, I covered a couple of talks that will happen during OpenObservabilityCon and OpenTelemetry Day. So that was the last collocated events that happened during OpenSource Summit. So one about the life of a span, the other one about the collector, a couple of recommendations about the OpenTree collectors in general. And then I had the chance to meet the team that is currently working on rewriting an OpenTelemetry collector into Rust, so called Rotel. So very exciting to get news about this project. I've been hearing about it. So now having the chance to meet the people working on it, that was very exciting. So if you enjoyed today's content, don't forget to like and subscribe to the channel. So follow me in Denver. Let's go to Denver for OpenSource Summit. First day at OpenSource Summit in Denver. Let's discover this conference.
Distinguished Architect at Red Hat Telco CTO office. So we are at the Open Source Summit North America in Denver, and I gave my presentation and speech yesterday about applied observability in the domain of telecom, especially observing, monitoring, and proactively operating 5G core networks together with the radio access side of the story. So the question is about just explaining how the layers of the application stack right now for the user plane and for the infrastructure and the platform and application layer. So as in the Kubernetes, we have control plane, if you're familiar with the control plane, and we have a user plane for applications to talk to other applications as well as other entities in the surrounding ecosystem. So for us, the telecom control plane is called signaling. That's our controlling plane. So the radio access that your phone is attaching, signaling with the radio system talks to 5G core, and 5G core authenticates you to either gonna allow you to attach to the radio network. If so, what spectrum, what's your subscription includes. Maybe your subscription is so low profile, they will not give you high speed, for example. So all goes through the signaling, which is called control plane in the 5G and 5G core. And when you really create a payload from your phone, say you're browsing the internet or looking at the Facebook or making a phone call, that is carried within the data pipe, which is called user plane. So that user plane usually don't go much in the cloud. It breaks out to the internet or the other interconnecting systems, so you can reach those web servers or services. So what are we observing here? So the question could be, we are trying to observe everything to be aware of what's going on in the network, of the telecom network, in the user plane as well as control plane. But we start at the control plane because that's the core fundamental DNA of the service architecture. So we look at, okay, how these applications are scaling. Are they able to authenticate the user? Are they able to enable terminals to attach? When you're attaching a terminal, it could be part of the, say, family plan or not, or separate subscription. So all happening on the control plane. Now we are going more into user plane to offer quality of experience, quality of service, improving your experience and your satisfaction. So what's coming in the pipeline is to remove the weakest chain in the operations, which is us, humans most of the time, to make it more data-driven decisions and applying the patterns, identify patterns. Say, hey, Henrik is open his phone and he has no bar, no connectivity. Oh, this is an abnormality because of the radio station nearby has a power outage. What can we do? Or we can resize this cellular network to serve Henrik with another base station nearby. So cellular networks, as in the name, is the cellular kind of complementing each other. We can increase the power signal to cover bigger areas or shrink the signal for small areas in a more granular way. We can dynamically adopt this based on abnormalities, based on the traffic demand, the popularity or density of the cell, and using AI behind the scenes. But to go AI, we have to have a proper data from control plane, user plane, collected through either application-driven data with OpenTelemetry and or with eBPF coming into a picture, filling the gap in the data story. So one of the key challenges in the industry is missing data points. We have data for CPU utilization, memory, I/O, but what is missing is the application layer, application-specific custom metrics. This is where we are trying to drill in using eBPF, with K-probes, with XDP, with C groups. This is the most critical part, to know what telco 5G is about the experience. Is it going down by means of radio signal? Is it going to go up because it's a sunny day? It's going to rain in 1 hour. We have to resize the cell, boost up the signal, all data-driven through application metrics. So the question is, what has changed in the last few years in the landscape of telecom technology, especially for 5G and the application stack? So as we have been moving from bare metal to virtualization, and virtualization to cloud-native network functions, we adopted the technology of the virtual machines first, and then we walked the path towards the cloud with containerization. Obviously, the best platform for container orchestration is Kubernetes by default, as we speak, and in the last few years it's like that. So having distributed applications with containers across the geography, not only one site, multiple sites, not one country, multiple countries, many platform teams able to maintain such a scale up and down dynamically has been really a problem because of the fact that there was no proper holistic observability solution in place. One of the intermediate or temporary solutions in place is to get or adopt the technology from per site, per country, and then stitch it together with the multi-tenancy, multi-vendor approach. That didn't really fly much because of the data incompatibility, because of the data pipelines are so proprietary. So we have been teaching and pushing the industry, in the telecom and media industry, with the community of observability as well as the cloud native application modernization practices. So adopting all this adaptive scaling for workloads, able to collect data by means of using service mesh, by using OpenTelemetry, and here comes eBPF because of the fact that we didn't go far with OpenTelemetry because that needed instrumentation in place within those applications. So eBPF data syncs into OpenTelemetry pipeline through collector, process the data, filtering, massaging, or segregating, or removing some pieces, or stitching some of them together for data mesh, and then exporting to, say, a Dynatrace dashboard, say a cold storage for regulatory purposes. So we are walking the path as we speak in the industry. So in the telecom industry, we used to have a lot of proprietary protocols such as TOP, which is telephone user part signaling, such as SS7. There comes the session initiation protocol, RFC 3261. And now we are evolved into less proprietary telecom specific protocols, but we have some still left, such as SCTP, a protocol that the radio stations use to register with the core network. Other than that, rest of them is pretty much based on, I would say, REST API or gRPC calls. So this is where 3GPP evolving the whole architecture based on cloud native practices. This is mostly gRPC and HTTPS interfaces. But we have few protocols left for sure to identify, say, I'm going to collect SCTP protocol details with eBPF to make sure that these radio stations, G-Node Bs, E-Node Bs, are able to properly connect. If not, I'm going to dump an eBPF data point to see what's going on with this protocol, for example.
It's the OpenObservabilityCon and OpenTelemetry today, so let's go.
Hello everyone, my name is Yuri. I'm co-founder of Holy Garden.
I am Jamie Danielson. I'm an engineer at Honeycomb, and I'm talking at Rotel Community Day about the life of a span. The life of a span is sort of funny. A lot of people don't really think about it, the amount of things that might happen during the life cycle of a span from start to finish, from it first being born, so to speak, from a tracer, to it going through processors and adding attributes and then getting exported and seeing the visualization in the back end. So there's a lot that actually happens during the life cycle of a span, and so I'm sort of excited to talk about it.
Most of people think about a span, about one tricky question in the observability area because, okay, you start a span and you finish that, but you don't know how much attributes you have to do that. You don't know if you have to propagate the context or how to propagate the context, instrumenting your application, following the best practices.
There's a couple of things that sort of inspired us to write this talk. One of the things was a post by our friend Gerasi, who had something about, I think maybe a life of a span or something similar from a few years ago. It's also something that I've had sort of in mind for a few years, thinking originally of something like a magic school bus, of looking through, this easy to understand sort of child's book sort of idea of going through this thing. But what tends to happen is people think about some of the big pieces of instrumentation. They think about the instrumentation library, they think about the collector, they think about some things, but there's so much that goes on in a span, in a trace, that by understanding more about how that works, it's better for end users to understand, especially if there's something wrong with their instrumentation or they're not sure what's going on, or they're looking for ways to enrich what they already have. And it's also useful for implementers, for SDK maintainers who maybe don't quite think about the details and the intricacies of what actually goes into a span. So we've been going back and forth and trying to figure out how to talk about the life of a span with our hero, Spanly. It's cute, it's silly. The idea is really to try and explain what can be a very technical topic into this silly story that makes it easy to understand and comprehend, but also helps you connect the silly parts to the technical parts. Figuring out how to break that up and split that up is kind of a tricky thing, and we might end up waiting to see what happens when it's time to give the talk and sort of just go by vibes. So I'll usually recommend, if people aren't sure where to start when they're instrumenting their application, starting with automatic instrumentation, or basically using an instrumentation library to instrument your HTTP requests, is a really great way to start because there's a lot of impact with not a whole lot of effort to get there. Once you start seeing your network requests in and out, then you can start getting a feel for where you might have gaps and where you might feel that you want to drill in deeper to understand, why did this take longer than I expected it to? So if you end up finding a span, for example, that takes a second and you thought it should be less, but you can't see anything below that, that's usually a good indication that there's more that you want to add to your application. So find some of the business logic that's happening in that service and see if you're able to add some instrumentation there. And conversely, if you end up seeing that you have a lot of extra spans or you have a lot going on that you can see in your backend, maybe you can get rid of some of those custom instrumentations. And what's nice is, depending on the language that you're using, especially Java, there's a lot of customization that you can do with the automatic instrumentation itself, where you can suppress different instrumentations and you can have less instrumented from the start. Once you're past that point, in the collector, you can also look at ways to reduce some of those spans or those traces that are coming through using things like a filter processor or the transform processor to get rid of some of the things that you realize you don't need.
In my second talk, we're gonna provide information to the audience on how to get a more reliable telemetry pipeline. Because what we've seen is people are taking care about the applications being reliable, but not the telemetry backend. So that means if you are not observing your OpenTelemetry collector with a couple of strategies like load balancer or queuing or rate limit, you can have your telemetry pipeline down in a situation that you can face some spikes in your observability traffic. Regarding the rate limit, we recommend to avoid a traffic spike, right? For example, if you allow your OpenTelemetry collector ingest, I don't know, 1,000 spans per second, then if you observe that the spike got 2,000 or 10,000, the data will be dropped to get your OpenTelemetry collector down. You have to see 2 points, right? The first one is taking care of rate limit on your application side before this data comes from to the OpenTelemetry collector. And after that, you can limit through, I don't know, batches or memory limiter to avoid your collector goes down. What we recommended during the call, we recommended basically 2 things. The first one, using the retry, and also the load balancer. First of all, you have to configure retry procedures, because your collector at the first message sent, the collector can behave not as expected. For that reason, you have to execute the retry option, and also load balancing traffic across different collector instances.
My name is Endre Sara. I am a co-founder at Cosly. So it is so much fun to be at this conference. I wanted to share our experiences in terms of the challenges that people have implementing and using OpenTelemetry. I started out describing how the increasing adoption of OpenTelemetry is generating a significant amount of data, resulting in both scalability and cost challenges. And today, the best practices are not to collect everything, or try not to collect everything, and just simply apply different sampling techniques and filtering techniques to throw away some data. But that actually ends up resulting in some of the gaps in the understanding of what are the services that are being observed, how they are communicating with each other. Because if you're sampling your good transactions, you don't know that those services are talking to each other. If you're not sampling your errors, it may look like that 90% of your signals are errors, but that's probably not true. So how do you actually better understand the behavior of the system? So there's 2 things that I wanted to emphasize in my presentation. One is the need for not just semantic convention, but building on top of semantic convention a definition of an ontology that can describe the identity of the entities, the components that make up your system, how they relate to each other, and what are their attributes, so that you get a picture of this is my environment, rather than just being able to reverse engineer it from raw observability data later. And then the second point that I made is how, while the common practice today is to try to create multiple pipelines to centralize all of that data into one central big data lake, which is a nice thing to do if you want to collect data, but if you actually want to be able to provide a scalable observability implementation, it's much better to be able to keep the data local, process the data at the edge, and take this semantic understanding of your services and the relevant signals instead of all of your raw data. So basically providing a better ontology and to be able to distribute that processing so that you get more scalable and a better understanding of your systems. The interesting question is, how do you capture this data? And this is where in my presentation I was referring to the Entity SIG. Because today, most of this information is captured in attributes of distributed traces. And it's very nice that there is some of the conventions on how do you refer to a server address or an HTTP URL, but those are only attributes on the span. What the Entity SIG is working on is creating a first-class signal representing the identity of these components as an entity with a reference to the resources. So now you actually have a proper first-class signal that describes that I have service A, I have service B, and then now you could say that based on the trace, I can see that these things are talking to each other with reference to the entities. So if we are able to, as part of the entities signal, capture the entities, capture the relationships, capture the semantic meaning of the relationships, suddenly we have a much better understanding of what is actually the system is made up of. And now that will empower us to be able to use the trace signals and the metric signals and the log signals with this much richer metadata than just the resource labels. I think that the most tactical, shortest path to be able to demonstrate this is to use the collector to generate these entities signal, but the intent within the SIG is to push this back into the SDK and have the actual instrumentation within the respective services emit the entities and emit the identification of those entities. So I think we're probably going to start with a collector, but then hopefully as it moves back into the SDK, push that back into the SDK and then the instrumented application to be able to emit the signal. Entity SIG has a weekly meetup, which is probably the best place to get involved. I should probably share some references specifically to the group. I am new to the group. There are a bunch of people who have been actively contributing. As I'm learning about the activity, I'm getting more excited and getting more involved, and I hope that other people will do the same. There is a lot of work in terms of both practically proving how this would work for like the first use case of Kubernetes, but then expand beyond just the Kubernetes use cases, how it first is dealing with the identity of the entities and the life cycle of these entities, how that expands into relationships, the definition of the relationships. There is a lot of backlog that the SIG has in front of it and a lot of opportunity to contribute.
My name is Mike Heffner. I'm a founder at Streamfold, and I've been working in observability for quite some time, and both as a vendor as well as a user, and excited to be building a new project that we think will help accelerate OpenTelemetry adoption.
I'm Ray Jenkins. I'm a founder at Streamfold. I've been working in observability for a large part of my career, interested in machine data, generally processing machine data at scale, ingesting, storing, and performing analytics on it. So.
Our session title was, that we talked today at the Rotel Community Day, was introducing a new lightweight, high-performance OpenTelemetry collector called Rotel. It's a project we've been working on for the last half year. And it's a new OpenTelemetry collector that's completely written in Rust, and we feel fills the needs for users working in resource-constrained environments, as well as looking for sort of higher performance, lower CPU usage, less memory usage from their OpenTelemetry collection. Why build another OpenTelemetry sort of data plane? There's the existing Rotel like reference collector out there, Fluentbit, Vector. We were seeing from users in our conversations that there were some domains that were just underserved by that. One in particular was the serverless environment. Users were trying to use the AWS Lambda layer there. and just not able to sort of use that because the cold start times are too high. Additionally, like you can translate that also to sort of large scale Kubernetes deployments. You attach a sidecar to all of your application pods. You know, if you scale that out at scale, then if you can save 100 megs or half a core from those at scale, that's real money. So we're seeing that sort of those needs, both myself and my co-founder Ray bring a lot of sort of systems level experience in the past, and we felt that, yeah, sort of starting from a first principles approach to building sort of a new collector from the ground up that was OpenTelemetry native would be, you know, helpful to the community and sort of fill some of these underserved domains.
Project's still really early. It's currently in alpha, and we have sort of, with that in mind, we've kept just the amount of features very thin and, you know, and small at first, so we can just focus on the goals that we spoke about, which was OpenTelemetry has a tremendous amount of interest in just a huge amount of adoption across, you know, the entire industry. And we're seeing and we're hearing, we talk to a lot of people in different domains that, you know, aren't the traditional, you know, SaaS, basically, infrastructure engineers, platform engineers, thinking, hey, I'm writing this, I'm building a product, I'm building an autonomous vehicle, I'm building an embedded system, I'm building this AI agentic, you know, platform. I'm going to immediately pull OpenTelemetry into this. This is like what their go-to for like when they think about instrumentation and observability. And they usually do quite well in terms of like getting the SDK going and starting getting rolling with that. But some of the other steps, like getting a full collector set up as like a sidecar to the application, that can be a bit confusing for some of these folks as they're developers. And historically, that's been a bit more of the purview of platform engineers and SREs. Sometimes they own that, you know, the collector and the configuration and the pipelines. So with Rotel, what we said is, let's just keep it real simple. There's just 3 pipelines out of the box. There's a logs, metrics, and traces pipeline. It's super simple to set it up, really lightweight. You can install it right from a Python module, and then, you know, you can write processors in Python. Just make it real easy for a different group of people who are maybe not that familiar with OpenTelemetry and the, you know, the reference implementation of the OTel collector.
Brief overview of Rotel. We have sort of your base foundational support. We can receive OpenTelemetry data. We can export OpenTelemetry data, all the sort of formats, HTTP, gRPC, et cetera. We have pipelines with automatic batching and retry support built in. We've been taking a really sort of user-driven focus to what we build, specifically on the exporter side. That's where we've been building sort of from user requests. So ClickHouse is you know, one exporter we built with full support for metrics, logs, traces. We also have early support for Datadog tracing, as well as AWS X-ray support for tracing. We also have in progress right now a PR, our first PR from a contributor that is going to add Parquet support, exporting that to the local disk, and then eventually S3. And yeah, we're really taking, I mean, part of being here today was to grow that community and see what people want from a sort of high performance collector, and really use that sort of feedback to sort of decide what to build next.
So right now, all the configuration is basically environment variable based and in command line args. So, and we don't support the Prometheus scraper. So right now the sources are, it's just OpenTelemetry sources. So OTLP, logs, metrics, and traces. But basically the getting going with it, it's pretty simple. If you go to the get started and look, starting it up and running, basically by default, it's going to be listening for OTLP on the standard ports. It's going to have those pipelines already set up for you, and then you're just specifying where you want to export that data. So it's really just sort of easy to get going. And that was part of the goal, because the collector is great and it's just got a tremendous amount of features, but that's a lot. If it's your first time looking at OpenTelemetry, it's a lot to get started. You got to learn about, you know, processors, you got to learn about pipelines, you got to learn about converters, you got to learn about like it was a lot. So we wanted to just try to reduce the footprint of that whole thing, reduce the surface area so people can get started quickly.
We've also been experimenting with integration directly into runtimes. So we can not only bundle into runtime packages like Python and Node.js, but we can build using Rust FFI processors natively in Python itself. So it gives users just a lot more sort of experience on the developer side to be able to incorporate OpenTelemetry collection into their application, moving the tooling sort of closer to developers.
Rotel is using about 75% less RAM than the OpenTelemetry collector for logs, metrics, and traces, with give or take a little bit. And then on the CPU side, generally Rotel uses about half the CPU. Yeah.
So for anybody that wants to try out Rotel, recommendation would be to go to rotel.dev. That's our main doc site. That also links to all the instructions for getting started. So we have Docker containers, we have an AWS Lambda layer that's available in all regions. We also are building binaries for all the releases that we make. And we also have, like I said, the bundled packages, so Python pip packages and NPM packages for Node.js.
My name is Denton Kreitz. I'm a sales engineer at BindPlane. I gave a talk today about a deep dive into the persistent queue, which is a component within the OpenTelemetry collector. So focused on how that adds resiliency and taking my experience as a customer-facing engineer to share some of the questions that I get asked and just help people better understand how to make use of the persistent queue. So the persistent queue is actually a part of the exporter helper that's in the core repo for the OTel collector. So these are functions and features that can be utilized by any exporter that implements those. And so that exporter helper contains retry logic as well as the sending queue, the persistent queue, and there's some new features that are also being added to it around batching, and I called some of that out as well in the talk. I wanted to talk about the core components of the queue, which are really the sending queue itself, as well as the file storage extensions. So both of those components have their own configurable pieces, and together they ultimately make up the persistent queue. So some of those configurable values are the size of the queue, and that's going to depend on the size of your data and how long you might anticipate or want to accommodate a particular outage. And then the file storage extensions also have their own configurations around where you would store that file, if it's like on disk, what folder, and so forth. There's also some settings around compaction, and that was one of the frequently asked questions that I went into to help folks understand why a particular file might look like it's not shrinking even though data is being dequeued. As with most of the components within the OTel collector, there are metrics and other telemetry that are emitted that help you get a better understanding of the functionality and health of your pipeline in general, as well as the specifics around the queue. So there are, I called out a couple core metrics within the presentation around the size of the queue, both the default capacity that's configured, as well as probably more importantly, the actual current size of the queue. So how much data is in it, and gave some general sort of recommendations around, even though the queue size might not be 0, the goal is that we wouldn't want to see it increasing unless there is actually an outage downstream. I think, again, going back to the idea of questions that I commonly get asked, I think one of the confusing points for a lot of folks is understanding how to think about the size of the queue in relation to disk size. So up to very recently, the queue is sized based on the number of batches, or as it's defined in the documentation, the number of requests. And so it can be challenging for folks to understand how does a number of batches equate to a certain amount of disk space, so that they can sort of understand, again, how to size that accordingly based on the storage that's available and how that would equate to a certain amount of time. So in the talk, I walk through some different ways to think about that. Again, going back to available metrics, the batch processor, there's a detailed metric that's available for the actual size of batches in bytes. So that's something that can be used to then get a size of the average batch, which then again you can sort of feed into your equation to understand, okay, how is that actually going to translate into bytes on disk?
That's it for today's episode related to the conference OpenSource Summit North America that happened a few weeks ago in Denver. So very excited to learn more about the 5G network and the differentiate with the user plane and control plane and where you should pay the different things that we should pay attention. And very excited to see that it's moving towards more Kubernetes and microservice environments, more easier at the end to somehow observe, even if we have, of course, to add eBPF probes and other things to instrument more the environment to get more details. The Life of a Span, amazing talk delivered, very interesting, very fun. So I will recommend to watch it, watch the recording on YouTube. The talk that was delivered on the OpenTree collector is also an amazing talk. There was in fact two of them, one more on the exporter and the queuing and everything. So I think very interesting to see that you can run into problems and maybe fine-tune a collector could make a lot of sense. And last, I think the project Rotel. I think the project Rotel, very interesting, a bit early phase as of now, but sounds very promising. And like they explained, it's not designed to be a getaway collector similar to the one that we're using on a daily basis, but more like a on-the-edge collector. So makes sense in Lambda functions or in very small edge devices to have a lighter version of the collector that will be there to collect and then send the data back to another gateway collector that will have more processors in place. But again, I think it deserves to be looked at it deeply, so I will try to look at it in another episodes and explain the value and how we can use it. If you enjoyed today's content, don't forget to like and subscribe to the channel. So see you soon for another episode. Bye.